Hello and welcome back to the alphabet of astronomy. Today it's brought to you by the letter P, and P is for parallax. So we've talked before about how difficult and important it is to be able to measure distances in space. For example, the discovery of these Cepheid variable stars that give us a standard candle to measure distances. But in order to use some sort of method like this, we need to be able to calibrate those brightness measurements, basically, with stars that we can measure the distance to directly. So how do we measure distances directly to stars? Enter parallax. So the basic idea behind parallax is that the position of an object relative to further away objects will appear to change as you move, basically. And this is really easily demonstrated by just holding your thumb out in front of you and closing one eye and kind of looking at your thumb relative to something far away and then changing your eyes. And notice how your thumb appears to be in a different position relative to that same thing, even though your thumb hasn't moved, just because you have distance between your two eyes. And you can move your thumb to different distances and see how that effect begins to change. And that it's bigger for when your thumb is closer and it's smaller when your thumb is farther away. This is one reason that having two eyes, or this binocular vision, is a very important part of humans' ability to have depth perception. Although it's possible to have depth perception with only one eye based off some other factors, parallax is a very important component of it. Stars, however, are a lot farther away than your thumb is ever going to be, and so we need a much bigger baseline. That is, we need a much bigger change in distance in order to have any hope of seeing this sort of relative change in position. Luckily, we have such a baseline built right in, because the Earth changes its position relative to the Sun every year, because we orbit it. And so if you look at the point that the Earth is at in its orbit, and then 6 months later it's basically on the other side of the Sun, 2 AU away from where it was. And so we have this kind of 2 AU built-in baseline that we can use. So if we measure the position of a star and then 6 months later measure the position of that star again and notice that it changes just a little bit compared to some other stars that don't seem to change, so those would be your more distant fixed objects, then we can measure the parallax of the star. Because at this point it just becomes a geometry problem, right? You just have a right triangle, you have your baseline which you know, and you have an angle which you measure, and then we know that that's how triangles work. And you can either basically do this, say, here's the Earth, it moved, here's a baseline, here's an angle that the star is moving, and so we need to solve for this distance. Or you can kind of flip it around and think of it just from the Earth's perspective, and that the Earth didn't move because, relatively speaking, from the Earth's perspective, it didn't move. And then the star moved, and so you can measure that angle down here, and then again, we would use the same baseline and solve for the distance. This is just some trigonometry here. And now we can solve for the long non-hypotenuse side, and that's the distance. That's as simple as parallax is. However, it's a lot simpler in concept than it is in execution. So even with this beautiful 2 AU baseline that we have, stars are still really, really far away. And so this parallax measurement is very, very small. We're talking tiny, tiny angles. We typically measure parallax with an angular unit called an arcsecond. Now there are 60 arcseconds in an arc minute, and there are 60 arc minutes in a degree, and of course there are 360 degrees in a circle. So an arcsecond is very, very, very small portion of a circle. And given these sorts of typical values that we're working with and how small they are, astronomers thought it was handy to come up with a unit that kind of encompassed this inherently. And so that is where the parsec comes from. So the parsec is a measure of distance, and it basically means 1 AU subtends 1 arcsecond, which means that the parallax of the star based on the Earth's orbit is 1 arcsecond, and that's a parsec. So by measuring the parallax angle, we can use that, and we basically know how far away something is in parsecs. Now remember that the parallax angle is going to get smaller as an object is farther away. So 1 arcsecond of parallax, we know it's a parsec away. At half of an arcsecond of parallax, then we know it's 2 parsecs away. So that's how that works. And so yes, parsecs are measures of distance, not time. I'm looking at you, Han Solo, prior to the Solo retcon. We all knew that that was a mistake. And just for reference, a parsec is equal to a little bit more than 3¼ light years, so it's a pretty far distance. So how far away can we actually measure this sort of parallax for stars? Well, with our very best ground-based astronomy, using cutting-edge technology, we can get down to about 0.01 arcseconds of accuracy in measuring the parallax of stars, which would put us out to about 100 parsecs away. Which is pretty far, that's 326 light years away, but it's really not that far, astronomically speaking. Now, going into space helps because the Earth's atmosphere makes it more difficult to measure these things very precisely. And so there was actually a recent mission from ESA called Gaia that was measuring the very precise distances and locations of all of these stars down to micro arcsecond, which is a millionth of an arcsecond precision in some cases. And so with Gaia data, we can really start to get out to, 1,000, 2,000 parsecs, depending on how bright the stars are. Brighter stars we can see more easily farther away. So this is really far. We're starting to get a pretty good sample here. We're talking over 6,500 light years from Earth, and Gaia is measuring out 96 million stars, so this is quite a lot that we're getting these sort of direct distance measurements for. However, even so, it's still only a small portion of the galaxy, and our galaxy is just one tiny little galaxy in the whole universe. Like, as we've talked about before, we measure distances extremely far out. So this calibration step of parallax is really, really key to being able to measure anything, even within our own galaxy, nevertheless something in another galaxy. So parallax is the fundamental way that we can directly measure distances in space. It's really important. It's a key first rung on this, what we call the distance ladder. And it's just a really cool concept, and it's pretty exciting. So I hope you learned a little bit more and understand a little bit better what parallax is and what a parsec is. Thank you so much for watching. I hope you will join us again for the letter Q, and I will see you again next time. Bye!